Welcome back. In today's video, we're going to derive the voltage division formula and the current division formula for two resistors in series and two resistors in parallel. Let's talk about the series and parallel circuits first. So in a parallel circuit, both resistors see the same voltage. However, they do not see the same current. The current is divided based on the resistance value. So it's only right for us to apply the current division formula to two resistors in parallel because they do not see the same current. The current is divided up within that combination. For the series circuit, each resistor see the same current. However, they do not see the same voltage. The voltage is divided according to the resistance value. So it's only right for us to apply the voltage division for the resistors in series. After we derive each of those formula, we're going to apply them on some previous problem that we did earlier. And we're going to apply the voltage division on the series problem. However, we're going to include another resistor to make that too. Okay, so let's derive the current division formula first. We start by finding the combination of the two resistors, and that is going to be the following. Take that to the power of -1. We simplify or combine whatever we have in the parentheses, and that will be R1 plus R2 all over R1 times R2, -1. That's going to equal to R1 times R2, R1 plus R2. So here we have the combination of both resistors. We can then, let's just write that down or draw the circuit for that. So here we have RP and VS. We can then let the voltage across the combination be. So that's going to be VS. I'll just use V. Let's just use V. Is equal to I, which you just put the S because we already have that, and times RP. So the voltage VS is equal to the current times the total resistance of the circuit. We can then go ahead and use the combination fact or the parallel fact that R1 sees the same voltage as R2 and both see the same voltage from the source. So then I1 is equal to, well, not I1, the voltage seen by R1 is equal to the current I1 times R1. And that's the same for I2 times R2, which is the voltage across R2. From those, we can then go ahead and derive the current through R1, which is equal to the voltage VS, which is the total voltage, because we remember that each resistor sees the same voltage as the source. So we can then go ahead and say that I1, the current through R1, is equal to the current from the source times the parallel combination divided by the resistance of R1. And that is going to equal to IS, the current from the source, times the parallel combination, which is R1 times R2. And then we include the R1 that we divided by over here. R2, R1 goes away. We're just left with IS times R2, R1 plus R2. So the current through R1 is equal to the current coming from the source multiplied by R2 all over R1 plus R2. So we can then go ahead and get the current for R2, which is equal to IS times R1 all over R1 plus R2. So that's the formula for the current division. And as you can see, if you're trying to find the current for R2, you multiply the current coming from the source times the other resistance, which is R1, all divided by R1 plus R2. Same thing, we can see that the resistors, the targeted resistor, so the current through the targeted resistor, which is R1, we see that R2, we see that the resistor in the numerator is changed. So if we want to find the current through R1, we use the resistor R2 in the numerator. Want to find the current through R2, we use the resistor in the numerator as R1. So we can then go ahead and derive the voltage division formula. For this one, we know that the combination is going to be R series, which is as simple as R1 plus R2. That then simplifies to the following, and that's now RS. We know that the current seen by each resistor is the same. So we can then go ahead and say that IS is equal to the voltage Vs divided by the total resistance Rs, which is equal to Vs divided by R1 plus R2. Now we can find the voltage division. So we know that the voltage across R1 is going to equal to the current IS times R1. That simplifies to IS. My bad. That's IS is equal to Vs over R1 plus R2. So that then goes to Vs R1 over R1 plus R2. And that's how you find the voltage across R1. Here we see that the targeted resistor is R1. We need to find the voltage across R1. In the numerator, we see that the numerator is the same as the targeted resistance. We see that VR2 is equal to IS times R2, which is going to be Vs times R2 all over R1 plus R2. So again, we see that the targeted resistor, so the voltage across R2, we see that in the numerator, we maintain that same resistor. So now that we have both formulas, we can then go ahead and apply it and see what the current and the voltage comes out to. So in the parallel circuit here, instead of using this formula in this case, 12 volts all over 2 ohms, we could just go ahead and say that the current through R1 is going to equal to, in this case, the current from the source. And remember that when it's parallel, the numerator is interchange. So then the numerator, so the targeted resistor will be different. So here we'd have R2 all over R1 plus R2. And that we could use to find the current through R1. However, though, notice that we did not use the voltage source. So we see that this equation, if we go back here and look, we see that this equation allows us to find the current when we do not know what the voltage source is, but we know what the current coming from the voltage source is. So here we see, we know the voltage source and we know the resistance of the targeted resistor, which is R1. Here we find the current through R1 by knowing the source current and the resistor values for each resistors. And that would give us the same current as 6 amperes. Now for a series circuit, I guess both of these are parallel, so we can just do series one down here. So for a series circuit, if we're using the 2 ohms, so let's say we have 2 ohms and 4 ohms, and the same voltage source of 12 volts, we know that RS is going to equal to R1 plus R2, which is 6 ohms. We know that I1 is equal to Vs, which is 12 volts. Let's just put 12 volts divided by the, well, just say, because they see the same current, so we can just say the total, which is Rs, which is just 6 ohms, and that will equal to 2 amperes. Because remember, resistors in series see the same current, correct? So the voltage across each resistor would now be V R1, which is equal to I1 times R1, which is equal to 4 volts, and the V R2, which would be still I1, because it's going to be the same, I1, see the same current. So we could actually just say this is the source current. I'll make that clear when I draw the circuit. Times R2 is equal to 8 volts. And we see that Vs is equal to V R1, voltage across R1, plus the voltage across R2, which is equal to 12 volts. This circuit is as follows. Just a series circuit. R1, R2, Vs, Is. So instead of finding the voltage, like what we just did, we're going to use the formula that we just derived. So pay attention that in this formula, we know the voltage and the resistor value. So we know the source voltage and the resistor values. However, notice that whenever we did it this way, we had to find the current. So what if we didn't want to try to find the current and we know the resistor values and the voltage source? We could just go ahead and apply our formula. So basically, remember that the targeted resistance, so V across R1, is going to equal to the voltage source times R1 divided by R1 plus R2. Or you could just say, where do we have it? The sum of resistance, which would be Rs. And that will give you the voltage across R1. And if you wanted the voltage across R2, same thing, Vs changes to R2 over Rs. And that will give you the voltage. So that's it for today's problem. See you in the next one. Bye.